whenever you.
Thank you, Francesca, for the introduction, and thank you for all the organizers for the invitation. Okay, so yes, I'll be talking to you about rank functions, but in the framework of higher homological algebra. So as many things in higher homological algebra, we can see something in classical homological algebra and ask, can it be generalized? And this is what we'll be doing today. So let's begin with the homological algebraic setting. So we fix a essentially small triangulated category T with suspension functor sigma, and then I denote the triangle by the collection of distinguished triangles. Now, Chuang and Lazarev in 2021 defined defined the notion of a rank function on a triangulated category T. Namely, it's going to be an assignment from the collection of morphisms of T to the non-negative real numbers, satisfying some axioms. Now, these axioms play very nicely with all of the structures we have, of course. Namely, it should be constant on isoclasses of morphisms. So the ranks of these morphisms should be the same if these morphisms are isomorphic. It plays nicely with the additive structure. So when you take two morphisms and you take the direct sum, the ranks of this new morphism should be the sum of the individual ranks. The third axiom plays nicely with this suspension functor, namely, if I apply suspension, the rank shouldn't change. And last but not least, given any two consecutive morphisms that are part of a distinguished triangle, so that means I have a distinguished triangle in front of me, and I got just two morphisms that are next to each other, I ask for an equation to be satisfied. Namely, they call it the rank nullity theorem, rank nullity equation, which says the rank of F minus the rank of the identity on Y plus the rank of G should equal to 0. Okay, so this is going to be the main object of study in the classical setting. And we're going to introduce one more definition, namely of a sigma additive function on T. There should be a sigma invariant additive function on T. Now, what are these things exactly? So first we consider additive functors on this additive covariant functors on the triangulated categories into the categories of abelian groups. And then we're considering a full subcategory of these finitely presented objects. I won't define it now, but the idea is supposed to feel like finitely presented modules. Now, an additive function on T, that's sigma invariant, will be an assignment from these finitely presented T modules into the non-negative real numbers, satisfying some equations. Namely, it should be constant on isoclasses. That's totally fine. And it should be additive on short exact sequences. Namely, given a short exact sequence in this small mod T category, so it is an abelian category, this following equation holds. And last but not least, the sigma invariantness is saying, well, I'm looking at functors going out of T. I can use sigma inverse to somehow go from T op to T op. And when I do this precomposition with sigma inverse, alpha should remain the same value on these two T modules. Okay, so one question you could ask, are there any connections between these two classes of things I've just defined? And in a four-author paper by Condi, Gorski, Mark, and Silverina in 2024, showed that actually these two classes of objects have a one-to-one correspondence between them. And it's an explicit correspondence that they give. There are explicitly defined maps. Now, the cool thing about this is they give this little tagline, well, in their paper, which is bringing the notion of rank functions to a functorial view. Now, you could ask yourself, well, right now already there's an explicit bijection, so already that's quite interesting. But you can ask yourself, what could this bijection give us? And in their paper, they show many, many multiple things that it can give you. The thing that I kind of want to focus on is that they show that you can answer such a question. Namely, what do rank functions actually capture? There is this ad hoc definition of a rank function. What is it actually doing on this triangulated category T? I'll give you some examples that will be a bit hand-wavy. So what do these rank functions, what can they capture? In some senses, they capture homological epimorphisms between DG algebras. In other cases, they can capture smashing subcategories with these nice quotients. And in other cases, they can also capture universal triangulated functors from your given triangulated category into smaller triangulated categories. So this is quite surprising, right? We have this rank functions notion, and it can capture these interesting structural things going on in your triangulated category between things. And so this is going to be the motivation as to why to bring this notion into the higher homological world, because then you may have maybe motivation to say that maybe these other universal functors we should study or can even study. So let's go higher into the higher homological world. So which environment do I talk about in higher homological algebra? Well, I'm going to be talking about the environment defined by Gaskell and Opperman in 2013, namely that of the D plus 2 angulated category, where D is a non-negative integer and also non-zero. So yeah. So what is it? It's three bits of data. We have an additive category, so it's very, very similar to triangulated categories. If you have never heard of these higher n angulated or D plus 2 angulated, it's very, very similar. So we start off with an additive category, which I'm going to call curly C. We have an autoequivalent, sigma D, and then we have a collection of distinguished D plus 2 angles. These are replacing the triangles. And this is what one would look like. This much longer. And obviously, this data is subject to some axioms, very similar to the triangulated category case. An example that will be of interest for us in this talk is an example that was done in the triangulated case by Amiot in 2007 and by Lin in 2019. Namely, the data I'm going to give you is the additive category will be projectors of an interesting finite dimensional algebra A. More specifically, this algebra should be D plus 2 twisted periodic algebra. In your mind, you only have to care right now that it means it's a self-injective nice algebra. Now that's our additive category. Now what's the other bits of information? Well, the definition of a D plus 2 twisted periodic algebra would come equipped with a sigma, this automorphism of the algebra. And this automorphism will give us an automorphism on proj A. Namely, it will be a tensor product with A considered as a bimodule. On the right, the normal multiplication is there, and that's this little one is signifying here. And the sigma inverse is saying instead of multiplying by A with normal multiplication, I'm going to twist it by using sigma inverse. And kind of briefly, which I'm not going to be very, very rigorous here, the D plus 2 angles are somehow projection resolutions in model A. This is not 100% accurate, but a lot of these, there are these functorial projective resolutions you can cook up, and these will give you some of these D plus 2 angles. Just a little list of some examples of what some of these twisted periodic algebras can look like. So there are a few of them, and you can get them quite easily. Okay, so this is our environment, and this is a typical example we're going to look at. Now, I'm going to try and now generalize the homological situation we had into this high level. So what we're going to do is we're going to forget about triangulated categories and look at B plus 2 angulated categories. So we replace the T's with a C, the triangles with these pentagons, and so on and so forth. The definition we saw second were these sigma invariant functions on T. And I just want to stress here that this definition will still work nicely if I replace T with a D plus 2 angulated category, which is what I've just done here. This mod C is still going to be abelian, so we can still look at additive functions on it. And the only thing we have to care about is that instead of looking at sigma inverse, I look at sigma dn. That's all. Now, more importantly, I guess, is that we have to care about what this notion of a rank function should be on now when T is a D plus 2 angulated category. Now, we want it to be an assignment on the morphisms of C. And you can kind of see the first two bullet points won't have to have any change because isomorphism classes and additivity had nothing to do with this higher structure. And the third bullet point, well, yes, there is a little, I don't know, physical change, but not much. It's just almost just notation at this point, right? We just replace it with the autoequivalence that we care about. Now, more importantly, we have to think about what this rank nullity theorem should be, how it should be replaced. And somewhat surprisingly, what I'm going to say is that the replacement will be looking at two consecutive morphisms in any D plus 2 angle. In other words, instead of requiring something longer, what I'm going to require is, given one of these long D plus 2 angles, look at two consecutive morphisms next to each other and require the rank nullity to satisfy with those two pairs. So you can think of this as a local rank nullity theorem, rank nullity equation. Okay, that's going to be our definition. And so the next question would be, well, how about the theorem, the four-author theorem? Does it still hold? And I'm here to say that in the case where C is these Amiot-Lin D plus 2 angulated categories, and when D is odd, the theorem does hold. So there is this functorial approach to rank functions on these D plus 2 angulated categories. Now, going from this, there are a few things I would want to think about. One, can this be generalized to arbitrary D plus 2, or essentially small D plus 2 angulated categories? And two, the questions about what rank functions capture, is this true? But this will be some future questions. So thank you very much.